Hey, what's up everyone? Terry here, Brainy Nerd Tutor, and I'm really excited to go through this video because we're going to cover a lot of material in this example here. We're going to go through exact differentials, Maxwell Relations, the Joule-Thomson Coefficient, PVT data, and equation of states and things like that. So we're going to derive an equation for the Joule-Thomson Coefficient in terms of PVT data using exact differentials and Maxwell Relations, and then once we have that equation, we're going to use it to determine if a gas obeying this equation of state and is subjected to a Joule-Thomson expansion, if the temperature will increase or decrease. So there's a lot of concepts here that's bridging your thermodynamic course material together, and I'm hoping to do it in a nice, beautiful derivation, and then also a follow-up problem from there. So let's begin. Let's jump right into it. Well, what is the Joule-Thomson coefficient? I'm going to move these down here. Well, the Joule-Thomson coefficient, that's our mu. It's the partial derivative of T with respect to P holding enthalpy constant. Now we want it not in terms of temperature, pressure, and enthalpy, but just in terms of PVT data for an equation of state. So how are we going to do that? Well, we're going to write the exact differential for enthalpy as a function of pressure and temperature. So if we do that, the exact differential for enthalpy in terms of pressure and temperature is dH. Now dH depends on pressure and temperature. So the change in enthalpy equals the change in enthalpy with respect to the pressure as the pressure changes, and the change in enthalpy with respect to how the temperature changes. Now this has to be under constant temperature, change in pressure with constant temperature, and then change in temperature with constant pressure here. So this is our exact differential here. This shows us how the enthalpy changes with respect to pressure, the slope, think of it graphically, and the change with respect to temperature, and then how those changes occur together is our kind of our total infinitesimal change in enthalpy, or dH, right here. So what's happening in a Joule-Thomson expansion? Well, that occurs under constant enthalpy. So constant enthalpy. So if we do a Joule-Thomson expansion, that occurs under constant enthalpy. So H equals constant. That means dH has to equal 0. So we're going to set this here, this thing, equal to 0. So we'll say 0 equals del partial H over partial P T dP plus change in enthalpy with respect to temperature, holding pressure constant. And this is defined as Cp. Here, that's defined as Cp. So we can plug that in. I'm going to give us a little bit more space here. So 0 equals del H over del P, temperature dP, plus Cp. This is T, this is a T, this is a P, this is a P, this is a Cp dt. We can see how the Joule-Thomson coefficient is the partial derivative of temperature with respect to pressure. Temperature with respect to pressure. So we're going to move this to the other side. Partial over partial P, temperature dP equals Cp dt. And then we'll divide both sides by dP and multiply both sides by negative, or divide both sides by negative dP. That's the same thing. Move this down. So we'll get the partial derivative of enthalpy with respect to pressure, holding temperature constant, equals Cp. Now these become partial derivatives because, this is a negative here, because we're holding enthalpy constant. We're holding enthalpy constant, and this here, this is our Joule-Thomson coefficient here. See that? So our change in enthalpy with respect to pressure holding temperature constant is equal to negative Cp times the Joule-Thomson coefficient. And we now have an expression. We can solve for the Joule-Thomson coefficient. I'll do it over here. So the Joule-Thomson coefficient equals negative, and then the partial change in enthalpy with respect to the pressure, holding temperature constant, all over Cp. Now this doesn't seem like it's helped us very much, but all we need to do to get an equation for a Joule-Thomson coefficient is to evaluate get an expression for this partial derivative here, this change in enthalpy with respect to pressure, holding temperature constant. And we're going to do that using another differential equation, or exact differential, for enthalpy. And we're going to look at one of the fundamental equations, enthalpy, in terms of entropy and pressure. So I'm going to get a different color here. And we're going to scroll down a little bit more, give myself a lot more space. And let's look at, so we have enthalpy, dH is T ds plus V dP. This is one of our fundamental equations. And we want the partial derivative of enthalpy with respect to pressure, holding temperature constant. So we have this fundamental equation here, and we want to divide both sides by dP. Now we're going to change these to partials, partial h over partial p. So we want to know the rate of change with respect to pressure, holding temperature constant. Now if we divide both sides, this right-hand side, by dP with temperature constant, temperature is a constant, so that gets pulled out. So then we have partial s over partial p, holding temperature constant. And we'll get this dP over dP relation here, but that's just one. That's just one. So we're left off with T times the partial derivative of entropy over the partial derivative of pressure, holding temperature constant, plus V here. So that's this relation here. And this, I'm just going to scroll up, the change in enthalpy over change in pressure, holding temperature constant. That's this right here. So we can substitute that in. So we'll take this expression and we'll substitute it into here. So Joule-Thomson coefficient equals negative, and this numerator is T partial S over partial P. So T partial S over partial P, entropy holding temperature constant, plus the volume. And all of that is divided by Cp. Did I get that right? Let me double check. Yep, I think that's good. Okay, so this is our equation for the Joule-Thomson coefficient, but we don't have it in terms of PVT data yet because we have entropy right here. So we need to find a relationship, another relation for this partial derivative. And we're going to use Maxwell's relations. So I'm going to scroll down a bit more, and we're going to look at another fundamental equation, which is dG equals VdP minus S dt. So this is another fundamental equation. We're going to write dG as an exact differential with respect to dP and dt in the other way. So this is it written as its kind of its fundamental equation, but we can also write it as a straight up change in dP, change in dt equation like we did before. So dt equals the change in G with respect to P, holding temperature constant, dP, plus dG over dt, holding pressure constant, dt. So this is our definition of an exact differential. The change in G, dG, is going to equal to its change with respect to pressure plus its change with respect to temperature here. And this is the same differential, but in terms of these quantities are being substituted in for these partial derivatives. But we can equate these two together using a really cool math trick, which we get. And the math trick is that the order of partial derivatives doesn't matter. So let's say you have f, and f is a function. And let's say f is a function of x and y. Okay? So it's a function of two variables. Well, we can take the derivative of f with respect to x, and we can also take the partial derivative of f with respect to y. Now, if we were to take, see this derivative of f with respect to x? Well, if we were to take its partial derivative with respect to y, so the partial derivative of that whole thing, I don't need the square brackets, but maybe I'll just lose the square brackets. That's equal to the partial derivative of this with respect to x. So if we can take the derivative with respect to x first, and then the partial derivative with respect to y. That's equal to, if we take the partial derivative with respect to y first, and then take the partial derivative with respect to x. It's pretty cool that it doesn't matter the order of derivatives for this. These are equal to each other. Why does that help us? Well, we have two relations here. See, we have this slope here, this rate of change with respect to p, g, and p here. That's equal to v in this case. So we can make these equal to each other. So partial v over partial p, temperature equals v. This has to be true because we have this v times dp, and then we have this partial term or factor times dp. So this is equal to this. And then similarly, this partial derivative has to be equal to negative s. So partial g over partial t, holding pressure, that has to equal negative s. So this instant rate of change has to be equal to this here. Okay, now see this? This is the derivative of g with respect to p, holding temperature constant, and this one's the derivative of g with respect to t, holding pressure constant. Well, why don't we take the derivative with respect to the other variable? If we do that, we would get the second derivative of g, but first we're taking the derivative with respect to p, and then we're taking the derivative with respect to t. That's going to be equal to the derivative of v with respect to t. Now we're going to hold pressure constant because we're taking the derivative with respect to t here. So first we're holding temperature constant, and then when we take the derivative with respect to temperature, we're holding pressure constant. And then the second relation, we're going to take the derivative first with respect to temperature, and then, I said temperature, but I wrote pressure, temperature, and then with respect to pressure. So we're going to take the derivative of this with respect to pressure, which is the same as taking the derivative of this negative partial s with respect to pressure. You don't really put the negative on the outside. Now, first we take the derivative with respect to temperature holding pressure constant. And then when we take the partial derivative with respect to pressure, we have to hold temperature constant here. And just like this relationship is true, here we have the same thing. We're taking the partial derivative with respect to g, first with pressure, then with temperature. In this case, it's with temperature first, then with pressure. So these two are equal to each other. These two must be equal. So the partial derivative of v with respect to temperature, holding pressure constant, has to be equal to the negative partial derivative of s over partial p, holding temperature constant. So this is a Maxwell relation. We can readily get this relationship from this one here. There's a little trick. If you look at this first term, it's the change in the v, flip over with respect to this one, and this is constant. So 1, 2, 3, partial derivative of v over partial derivative of t, holding p constant, and then in s, we start here, is equal to the negative partial derivative of s with respect to v, holding temperature constant. So we kind of if you know that order, then you can get this Maxwell relation right away. But otherwise, this is the full derivation. And why did we do this? Well, see this partial derivative of entropy with respect to pressure holding. Oh, see this? There's a pressure here. Temperature here. I should put this. This shouldn't be pressure. This should be temperature. This is temperature, so this one, this is temperature. This is the same thing. Okay. Well, this change in entropy with respect to pressure holding temperature constant, that's, I'm going to scroll way up. That's this thing right here. So I'm going to, let's remember this here. Or maybe I can copy it. And I'll paste it down here. Okay, paste it down here. So I'm going to substitute this into here. Now this negative here, got to remember this negative is with respect to the numerator. I plug that in. I don't want to lose that negative. So this is temperature, and this partial S over partial P, entropy and pressure, that's this. So that's the negative partial V over partial T holding pressure constant plus volume. And all of that is divided by CP. And that's pretty much it. We're going to clean it up. We have everything in terms of PVT data, or variables. So proudly we'll write the Joule-Thomson coefficient is equal to, now this, we'll move this negative in here, so this becomes positive. So it'll be T times the partial derivative of volume with respect to temperature, holding pressure constant, plus minus, because this negative goes here, feed the chickens, some people say, distribute the negative in, so minus V, just going to put everything in blue color, so it's a little cleaner. There we go. So that's the Joule-Thomson coefficient in terms of pressure, volume, and temperature there. Awesome. We went through exact differentials. We went through Maxwell relations. Now we're going to use this to solve a problem. So we're going to bring our example question here. And question is, if a gas obeying the equation of state, P times V minus NB equals nRT, is subjected to Joule-Thomson expansion, determine if the temperature will increase or decrease. Okay, let's look at this here. So we have this Joule-Thomson coefficient, and then we'll qualitatively determine if that's right or not. We need to plug this in. Well, first we need to deal with this partial. So let's do this derivative. So the partial V, partial T holding pressure constant, we're taking the derivative with respect to temperature of volume. And what is volume? Oh, we need to solve for volume first. So let's solve for volume here. We'll divide both sides by P. So V minus NB equals nRT over P. And add NB to the other side. So V equals nRT over P plus NB. And we'll take the derivative of that, nRT over P plus NB. Doesn't have to be square brackets, I guess. We can keep the parentheses. And this is holding pressure constant. We'll take the derivative with respect to T of each term separately. So this is just a constant times T, really, because all of these are constant. So they're just equal to the constant. So nR over P. And both of these are constant. The derivative of a constant with respect to any variable, that's 0. So this is our partial derivative with respect to temperature here. And we can plug that into our equation for our Joule-Thomson expansion coefficient. So temperature times nR over P minus V over CP. Okay, so that's nRT over P minus V over CV. Okay, so here, now before we continue, if this was an ideal gas or a perfect gas, then this value would be 0. Just on an aside. See, remember PV equals nRT? Well, that means V equals nRT over P. nRT over P is V for an ideal gas. I'll write this here, ideal gas. So this left-hand term in the numerator is V. V minus V is 0. So the Joule-Thomson expansion coefficient would be 0, and it is 0 for an ideal gas. That means when a gas expands isenthalpically, so with constant enthalpy, then it won't increase or decrease in temperature. And it increases or decreases in temperature due to intermolecular forces. Since an ideal gas assumes that there's no intermolecular forces between the particles, then it doesn't experience a change in temperature for Joule-Thomson. For an ideal gas, this is 0. But for us, we don't have an ideal gas or a perfect gas. We have this type of a gas. And nRT over P, if we were to solve that, nRT over P, what is nRT over P? Well, let's subtract, that's this right here, actually, we already did it. nRT over P equals V minus NB. So we're going to substitute that in. nRT over P, that's this, nRT over P, so that equals V minus NB. Minus V over CV. Okay, well, V minus V is 0, so this is negative NB, I'll make it all one color, over CV, mu. Now, assuming B is positive, and if you know about this equation of state, B represents the size or of the molecules, or represents the repulsion, is related to the repulsion forces. So B can't be negative. So that means this whole thing is greater than 0. So mu is greater than 0 here. Oh, less than 0. What am I saying? Negative is less than 0, isn't it? Negative is, so mu is less than 0. And change in temperature over change in pressure under isenthalpic conditions. This is mu, and this is less than 0. So when you think about increasing the pressure, the temperature goes down. If we think about this. So if we think about a plot here, temperature versus pressure under constant enthalpy, the slope is going to be less than 0. Now if this is constant, it'll be like a constant slope here. So if we increase the pressure, the temperature goes down, and with a Joule-Thomson expansion, we're pushing gas. This is gas here. We're pushing it through a throttle. So like we're forcing it through a porous substance or a very small hole or things like that, and it's going from and we're pushing it against some external pressure here, and it's expanding. So we're going from a higher pressure to a lower pressure. So in this case, we're going from a higher pressure to a lower pressure during a Joule-Thomson expansion. Well, if the Joule-Thomson coefficient is less than 0, that means when we go from a higher pressure to a lower pressure, the temperature is increasing. The temperature is increasing. So we're going from like an area of really more compressed. There's a hole here. And we're going to an area that is more spacious. We're separating those molecules, the gas molecules, and the separation causes an increase in temperature. Well, how can that happen? Well, why is the temperature increasing when they're expanding? Usually when the pressure decreases, we expect the temperature to decrease as well. That's if we think of PV equals nRT. But in this case, the temperature is increasing. And why that's the case is because this is a real gas in which the size or the space between the molecules is significant. Okay, it's very significant. So we have molecules that are squished together. And when these molecules are squished together, they repel each other. Think of intermolecular interactions between the molecules as springs. Okay? And if you have molecules that are really compressed, then it's like you're compressing a spring between them. And they're in a state of high potential energy. The intermolecular, there's high potential energy because we've squished them together. They're experiencing repulsive forces that want to push them apart. You could think of it also as like magnets. Say you have two south magnets. You're trying to push those magnets together. They don't want to come together because they repel each other. So it takes energy to keep them together. And that energy is potential energy stored within those intermolecular bonds. Well, when they expand, what happens to that potential energy? Well, that potential energy is relieved. Our spring is being restored back to more of an equilibrium state, if you will. Or those magnets are being pulled, they're not being pulled away from each other, they want to go away from each other. So as they go away from each other, it takes less force to hold these magnets together. So we've decreased the potential energy. Where did the potential energy go? If we relieved some of the potential energy here by reducing the compression between them, well, that potential energy turned into kinetic energy. Imagine the spring being released. Those molecules are going to separate from each other and they're going to move faster. Well, if they move faster, then their average kinetic energy is going to increase, and average kinetic energy is related to temperature. So in this case, with this real gas in which size is significant, it's highly compressed, intermolecular attraction is not significant, they're compressed, we see an increase in temperature when it undergoes the Joule-Thomson expansion. Alright, that was a lot of material. We covered a lot of ground with exact differentials and Maxwell Relations and the Joule-Thomson Coefficient, and even got deep into this molecular interpretation of it all. Hope you enjoyed it. Thanks again. If this was beneficial, please like the video because it'll motivate me to make more, and I'll see you in the next one. Cheers.